That's good. Right, we'll make a start. So as you can see, title of this presentation is Marine Corrosion and Protection. So I just want to welcome everyone to this presentation and say a thank you to Simon and John and all the committee members of EMMS for inviting me to make this presentation. So I hope you all enjoy it, and I've been asked to present for about 45 minutes, so I'm going to finish about 8 o'clock ish, so I'll try not to run over the time. So as you can all probably aware, this topic is quite a big topic on marine corrosion, so obviously I'm not going to cover every aspect, but what I've done is picked out certain points on marine corrosion that hopefully will be of interest to you. So looking at the agenda for my presentation, I just want to say a few words about the Marine Corrosion Forum, and then look at the marine environment, and then look at how we mitigate marine corrosion issues in the field, and then look at a few case studies or specific examples. So the first is looking at accelerated low water corrosion. Then I want to look at cathodic protection of offshore wind structures, and then look at hydrogen-induced stress cracking resulting from cathodic protection. So those two are sort of linked together. And then moving on, looking at microbial induced corrosion of copper nickel tube marine coolers. And then I want to finally look at corrosion issues with seawater cooling systems. So just want to say a few words about the Marine Corrosion Forum. So it was initially created in 1988 as the Marine Corrosion Club by a group of companies with an interest in marine corrosion. So the Marine Corrosion Forum holds 4 meetings a year, and before the pandemic we had 2 meetings in London, 1 in Birmingham and 1 in Aberdeen, which was a joint meeting with ICOR Aberdeen branch. During the pandemic we've continued to hold these meetings online in collaboration with the Aberdeen branch of ICOR. So they've been very successful, and we've had our meetings attended by 80 to 100 people who have joined the webinars on our meetings. So the forum is a non-profit organisation with the aim of discussing and disseminating knowledge on marine corrosion and more widely wet corrosion issues relevant to industry. So typically 4 presentations are held at each of our meetings, which are recognised by IOM3, ICOR, IMRS for CPD hours. So this presentation includes topics that have been discussed at Marine Corrosion Forum meetings, with contributions by several of the members and presenters. So the Marine Corrosion Forum currently has about 34 industrial members from a wide range of sectors, as you can see by the spread of logos that we've got on this slide. So firstly, I want to discuss and look at the marine environment. So in sort of clockwise order, I want to cover the effects of temperature, salinity and pH, dissolved oxygen, the influence of tidal and wave actions, the influence of macrofouling and the biofilm and microbial induced corrosion, and then the influence of pollutants, for example, hydrogen sulfide, and then finally looking at the marine atmosphere. So all of these factors can contribute to marine corrosion, and many of these need to be taken into account if you're selecting materials for applications in marine corrosion or in seawater. So I just want to start and look at temperature, and look at the left-hand picture here shows the temperature distribution of the seas across the globe, And it's not unsurprising to see that there's a big temperature differential between the sort of Arctic areas here and the equatorial areas here, where you can get a temperature difference between close to freezing up to about 35 degrees. So obviously this is a big consideration in applications for marine corrosion, depending on where the metals are being deployed around the globe. And then in addition to the surface sea temperatures, there's a temperature variation going down the depth of the sea. So at the surface you've got the highest temperatures, and then you get a fairly steep decline in the temperature through this thermocline region down to about 1,000 meters. And round about that region, the temperature is round about 4 or 5 degrees, and it doesn't change a huge amount as you go increasing depth. So this is a big consideration, again, for structures or materials in marine environments, whether you're using them in the surface regions or whether they're deployed at the seabed. So the temperature can be significantly different. So next, I just want to say a few words about salinity. So this map shows the variation in salinity around the globe, and the salinity doesn't vary a huge amount, with an average of 35 parts per thousand, which equates to about 19,400 milligrams per litre of chloride in the seawater environment. So next, I want to look at dissolved oxygen. So as many of you who are familiar with corrosion, oxygen can play a big role in corrosion. So the dissolved oxygen in the seawater environment is a big consideration. And this map shows the dissolved oxygen concentration around the globe. And generally it follows the pattern for the surface sea temperatures, because the oxygen is dependent on the oxygen in the environment, which is fixed at about 20.8%, and then the solubility of oxygen in the seawater is then dependent on the temperature of the seawater, with the lower temperature having the highest solubility of dissolved oxygen. So for going then through the depth of the sea, at the surface, although the temperature is higher, the dissolved oxygen is also higher. And this is because you've got the air with 20.8% oxygen close to the surface of the sea. So that's obviously picking up a lot of oxygen from the air. So as you go down, you get a steep decrease in the dissolved oxygen, and then it's fairly stable as you go deeper. And this sketch illustrates the difference between the Pacific Ocean and the Atlantic Ocean in the actual dissolved oxygen content. So if we're looking at oxygen, there's certain areas around the world where there's a depletion in oxygen, which is called anoxia or hypoxia. And in these regions, the presence of hydrogen sulfide is normally associated with these anoxia or hypoxia regions due to the anaerobic conditions. So hydrogen sulfide is formed by the presence of anaerobic sulfate reducing bacteria, or SRB, and the presence of SRBs is a main reason for microbial induced corrosion of metals in marine environments. So H2S can also be a contributory factor in hydrogen-induced stress cracking associated with CP, which I'll cover a bit later on in this presentation. So related to dissolved oxygen, some of the inland seas, examples here, the Baltic Sea and the Black Sea, have anoxia regions in these seas where there's very low oxygen concentrations or zero oxygen concentrations. And this results in SRB activity at the seabed. So there is a risk of hydrogen sulfide cracking of carbon steel subsea pipelines where the sour environment is on the OD surface due to the anaerobic SRB activity. So to qualify pipelines which have been put across the Black Sea, so there's the Blue Stream pipeline that was put between Russia and Turkey about 20 years ago, and also the Turk Stream or South Stream pipeline that went between Russia and Bulgaria more recently. And then there's the pipelines in the Baltic Sea, the Nord Stream pipeline from Russia to Germany. So these pipelines were subsea pipelines where full ring testing was carried out to qualify the material for welds, and these tests were conducted for the Blue Stream, Turk Stream and the Nord Stream projects. And the photograph here shows one of the test specimens that was used on the 48-inch diameter pipe that went across the Baltic Sea here on the Nord Stream project. And this project was subject to a presentation at the Marine Corrosion Forum in 2013 by CEng. So keeping on the topic of oxygen, the action of waves and tides creates distinct zones in marine steel structures. So this sketch here shows the relative corrosion or loss in metal thickness of a carbon steel going through this tidal zone from the atmosphere, going down through the splash zone, through the tidal zone, and then into the submerged region. So these regions can be split into several zones. So zone 1 is exposed to marine atmospheres. So steels in this region would be protected by coatings. In zone 2, which is a spray or splash zone above the mean high tide level, this would be the most severely attacked region due to continuous contact with highly aerated seawater and the erosive effect of spray, waves and tidal actions. So this region would need to be protected by coatings and at times by claddings and sheathings. And Monel 400 and also 9010 copper nickel have been used as sheathings to protect steel in this region. So in zone 3, which is a tidal zone, and this is a zone between the mean high tide and the mean low tide. So the corrosion rates can be very high at a position just below the mean low tide in a region which is very anodic relative to the tidal zone. And this is due to differential aeration cells which form in the well aerated tidal region. In this region, the steel would need to be protected by coatings and cathodic protection. In the zone 4, which is continuously submerged, the steel would be protected by coatings and CP. If we now look at macrofouling, so macrofouling is the build-up of marine growth, which can be oysters, barnacles, etc., on the metal surface. So the extent of macrofouling is dependent firstly on the metal. So copper alloys are widely used in marine environments because they have an inherent high resistance to biofouling and particularly to macrofouling. So the other factors to consider are the water temperature and the pH, the content of organisms in the water, and also the flow rate. So the stagnant conditions provide the most desirable conditions for the growth of these marine bodies. So macrofouling can lead to corrosion due to crevice formation and also due to creation of oxygen concentration cells and also due to local changes in pH. So the photograph here shows macrofouling on a titanium heat exchanger inlet. So I just want to now talk about the biofilm. So a thin microbial slime layer forms relatively quickly on inert surfaces of metals in natural seawater, which is a precursor to macrofouling and is known as a biofilm. So for stainless steels, the biofilm has a strong catalytic effect on the cathodic reaction, which is a reduction of dissolved oxygen. So the action of the biofilm results in an increase in the corrosion potential to approximately 300 millivolts over a few days to a few weeks. A high corrosion potential increases the risk of crevice and pitting corrosion of stainless steels. So this graph here shows the effect of the biofilm on stainless steels in natural seawater here, where they'd follow this path where the potential would increase to around about the 300 millivolt region, whereas in artificial seawater you get a small increase but not a significant increase in this potential. So the result of this ennoblement of the stainless steels is that natural living water is therefore considerably more corrosive than artificial seawater or sodium chloride solutions. So the catalytic influence of the biofilm is affected by temperature, and at 35 to 40 degrees the biofilm is killed and the effect vanishes. And this is illustrated by this graph, which shows that at the temperatures of 9 degrees, 24 degrees, 18 degrees, you get the ennoblement of the stainless steel up to about 300 millivolts due to the biofilm, whereas at the higher temperature you only get a small effect, and at an even higher temperature you get a very negligible effect on any potential increase. So just want to look at marine atmospheres on corrosivity, and this map shows a corrosivity index for a steel going from 1 up to 8. So 1 where you'd get very little corrosion, up to 8 where you get high amount of corrosion. And you can see around the globe there is a variation in this corrosivity from very mild areas here at the tip of South America, for example, up to some more corrosive regions here in the Far East. And this is related partly to pollution and also partly due to the environment and the temperature and humidity and condensation during changes in temperature from day to night. I now want to look at the first case study, and this is a extract from a presentation that was made by Belinda Gay from Sandvik, and this was presented at the Marine Corrosion Forum in January 2020. And the presentation was looking at material selection for hydraulic and instrument tubing systems in marine environments. So for inland application, standard 316L or even 304L grades of stainless steel will give sufficient corrosion resistance. For harsher locally environments, though, a higher alloyed material may be needed. So for marine environments, for coastal or marine environments, higher alloyed materials are usually employed. And this is due to the effects of sea spray and chloride deposits, which increases the risk of pitting and crevice corrosion. And also there may be a risk of chloride-induced stress corrosion cracking in the worst case examples. So the work conducted by Sandvik was to conduct some exposure testing at 2 locations, one on the Swedish west coast, which was considered to be a temperate climate, and the other one was in Florida, which was a tropical climate. So I'm jumping through the presentations and going to the conclusions. So the conclusions were at the Swedish west coast, which was a temperate climate. The 316L stainless steel with about 2.6% molybdenum does not have good enough corrosion resistance. So the alloy 825, which has a high nickel content, has even worse corrosion resistance in this environment than 316L. So the 904L, which is a superaustenitic grade of stainless steel, could possibly be an alternative to 316L or 825, since it only showed some staining after 1 year of testing. So the Super Duplex, which is a 25 chrome duplex, a 2507 grade, showed excellent resistance to corrosion, and this would have been the best material choice for the temperate climate. So in the tropical climate, the 316L, unsurprisingly, did not have good enough corrosion resistance. And also the alloy 825 was even worse than the 316L. So the 904L did not provide an alternative under these tropical conditions, because it showed pitting after 1 year of exposure. So under these tropical climate conditions, the only choice of material would be the Super Duplex 25% chromium grade, which showed excellent corrosion resistance. So I now want to just say a few words about the mitigation of corrosion in marine environments. So I've split this into 4 areas. So the first option is to select a corrosion resistant metal. And the choice in marine environments is normally between stainless steels, nickel alloys, copper alloys, aluminium alloys, or titanium. So the other option would be if using carbon steels in immersed seawater environments, the carbon steel would need to be protected by applying coating and also cathodic protection. And the important things to consider on the coating would be the surface preparation, how the material is prepared, and also selecting the correct coating. And then on the CP, the important issue to look at is the design of that CP system, which I'll be talking about later on in the presentation. So the other option, if using carbon steels exposed to marine atmospheres, you'd need to apply a coating. And again, important to consider the preparation of the steel and also the selection of the actual coating material. So the fourth option is really confined to seawater piping systems, where you can modify the environment using chlorination to combat the threat of microbial induced corrosion, and also to stop macrofouling occurring on the tubes. And the other option is to deaerate the seawater to remove oxygen. So I now want to look at another example or case study, which is accelerated low water corrosion. So this is an aggressive form of microbially induced corrosion, or MIC, that may occur on steel in estuarine and marine structures. So corrosion rates on steel as high as 1 millimetre a year have been reported, and the major threat to marine and coastal infrastructure internationally. So both sulfate reducing bacteria, or SRB, and sulfur oxidizing bacteria, SOB, have been linked to this form of accelerated low water corrosion. So the factors to consider include marine nutrient contamination in promoting microbial activity, and the electrochemical environment within this intertidal zone. So these photographs show examples of what you would see if you had accelerated low water corrosion. So these photographs at the top show examples of this corrosion on marine sheet pile walls, where you get severe corrosion of the steel that you can see in these examples. So this corrosion can take the form of non-uniform corrosion above the low water line here, shown from this photograph, or non-uniform corrosion below the water line. So these slides were provided by Brian Wyatt of Corrosion Control Limited, who's a member of the Marine Corrosion Forum. So Brian posed the question, is cathodic protection a solution for ALWC? So in 1998, accelerated low water corrosion was causing unexpected and early structural distress to, in particular, sheet steel piled facilities in UK ports and harbours, as I've just illustrated. So accelerated low water corrosion was controversial, and the solution was being debated. So there's a few questions to address. So the first, what was the most cost-effective solution to prevent accelerated low water corrosion? And the answer would be cathodic protection. So can cathodic protection prevent ALWC? And the answer would be yes, it can. And can cathodic protection stop any established ALWC? Yes, it can, but higher currents are required and it would take time. And next question would be, can you use galvanic or sacrificial anodes, and are these as effective as impressed current? So the answer to this would be yes. And finally, what level of cathodic protection would be required to prevent ALWC? So a potential of minus 900 millivolts against a silver chloride reference electrode would need to be applied to prevent this form of corrosion. So I want to stay on the theme of cathodic protection and present some slides, some information from a presentation that was made by Brian Wyatt to the EFC conference in September last year, and the title of the presentation was Cathodic Protection of Offshore Renewable Energy Infrastructure. So I'd also like to acknowledge a couple of the other presenters, which was Jim Preston from Corrosion Control Affiliates Limited, and also Robin Jacob from the CP Consultancy Limited. So this presentation was also made to the Marine Corrosion Forum in October 2019. So firstly, as an introduction, I just want to look at areas of corrosion concern on offshore wind structures. So most of you are familiar with these type of structures. I'm sure you've seen photographs of them. So these sketches show a section through the structure. So if we look at the external surfaces, what we need to do, so in the atmospheric zone above the seawater, we'd need to apply coatings to protect the transition piece here. And then in the splash zone region, just above the water zone, we'd need to apply coatings again and have some additional corrosion allowance because of the severity of the environment. And then if we move down the monopile below the waterline in the submerged zone, we'd need to apply cathodic protection and coatings as well. And then in the mudline zone and the buried zone, there is a risk in these regions of sulfate reducing bacteria activity depending on the particular environment. If we then look at the internal surfaces of the structure, so in the upper reaches, you can get some condensation of seawater, so you need to protect these surfaces with coatings. And then if we move down to the internal surfaces of the monopile, so these would be typically flooded with seawater, so they would be protected using coatings and cathodic protection. And they can also be subjected to sulfate reducing bacteria activity. So this is a potential risk in these regions that you get this microbial corrosion occurring, and this can also occur down below the seawater in the mudline zone. So now just want to look at some factors that we need to consider on the cathodic protection system. So firstly, it's useful to review what has gone before. This is from ASTM Metals Handbook Volume 13, based on work in the 1950s. So to a first approximation, the CP current requirement is proportional to the corrosion rate, which in turn depends on the rate of oxygen access to the surface structure. So in low flow conditions in seawater, uncoated carbon steel corrodes at an average rate of about 0.13 millimeters a year, with localized pitting about twice the average, as shown this point on the graph. So the water velocity significantly affects the corrosion rate, and at high velocity, or high flow conditions, which increase oxygenation at the metal surface, higher rates of attack will occur. So rates of greater than 0.8 millimeter a year have been reported at these high flow rates of 5.5 meters per second. So looking at flow rates and the actual current densities that need to be used for cathodic protection systems, you can see from this graph that as the flow rate increases, the current demand on the CP system also increases. And the big difference between these two lines is due to the formation of calcareous deposits on the steel structure, which typically occur on cathodic protection systems. So over time, normally calcareous deposits are formed, which reduce the current demand on the system. Now I want to look at the effect of wave height on the cathodic protection system. So you can see here that as the wave height increases, the potential here on the CP system decreases. And this is also shown on this graph here from going back to 1979, that shows that as you got high wave height action, you get a reduced in the cathodic protection potential. So this means that any potential surveys in calm summer days will not inform the performance of the CP system in winter storms, and the variations may be greater than 50 millivolts. So it's wise to use these Met-Ocean reports to look at the wave, sea level and sea current when designing your cathodic protection system. So for convenience and the critical need to minimise costs of installation, it is common to distribute external anodes on a CP system as a circular array on the bottom of the transition piece, despite DNV GL recommended practice B401, stating that anodes shall be distributed to provide a uniform current distribution. So closely grouped anodes have available current output much less than when they are widely spaced. So this can and has resulted in inadequate protection of offshore wind structures. So due to attenuation down the monopile, the distribution of current from the anodes at a single level can be problematic for water depths greater than about 15 meters on bare monopiles. leading to extreme non-uniformity in the protection potentials achieved and inadequate protection remote from the anodes, often near the seabed, where fatigue loads and sensitivity to corrosion fatigue are greatest. So this has occurred in practice. And an example I'm going to show in the next few slides. So the design of this anode configuration shown here was considered to be compliant with the DNV recommended practice B401. However, actual performance and modelling indicated otherwise. So all of the anodes calculated as RP B401 for current and life are placed as 3 rings on the transition piece shown here, and also shown here on the model. So under the conditions modelled, a large part of the monopile structure is predicted to be underprotected, which not meeting the design potential criterion of -900 millivolts to protect against corrosion and against microbial induced corrosion, as shown on this model. So also the area close to the mud line is less negative than -800 millivolts. So this would mean it would not be protected against corrosion. However, using the same number of anodes under the same external conditions, but relocating some anodes to rings lower down on the monopile resulted in full protection modelled over the whole of the monopile surface with a least negative potential of -940 millivolts. And that's shown on this model here, which shows that the least negative potential is -940 millivolts. So next, just want to say a few words about electrical bonding. So where anodes are mounted on the transition piece, but intended to protect the monopile surface below, it's essential to ensure an electrically conducting path of very low resistance between the two. So this photograph here shows the transition piece here with the rubber seal to retain the grout. So low resistance electrical bonding is needed between the transition piece and the monopile. So I'm going to skip this slide because of time and move on to discuss hydrogen-induced stress cracking. So HISC is related to hydrogen generation from the cathodic protection system in marine environments. So many of you will be familiar with this Venn diagram that's used to look at stress corrosion cracking. So for HISC, we need to consider the material and whether we have a susceptible material and microstructure. We also need to look at the stress and whether the stress is in a critical region. And finally, we need to look at the source of hydrogen from the CP system. So now if we look at those 3 factors in a bit more detail. So the material factor is, firstly, we need to look at what are the susceptible materials for HISC. So these are high strength steels, weldable martensitic stainless steels, duplex stainless steels, and precipitation hardened nickel based alloys such as alloys 718 and 725. Also on the material, we need to consider the microstructure, the hardness, the strength level, and if the material has been subjected to any cold work. On the stress factor, we need to look at high local stresses and if there's any residual stresses associated in particular with welds. So if we come to the hydrogen factor, we can split these into 2. So the first is the hydrogen generation, and this is due to the cathodic protection system and overprotection or 2 negative values generating hydrogen at the cathode. And then we can look at hydrogen absorption into the materials, and this is really dictated by firstly the amount of hydrogen that we've got at the surface and also the presence of hydrogen sulfide in the environment, the temperature, and also the hydrostatic pressure. So at the cathode, the material we're protecting, either the steel, the duplex stainless steel, we get the cathodic reduction reaction, which can be the reduction of water to form hydrogen and hydroxide, or the reduction of hydrogen ions in the solution to form hydrogen atoms. So these hydrogen atoms, which are adsorbed onto the surface of the metal, can then be absorbed into the metal, or they can recombine on the surface to form hydrogen gas that will then bubble off the surface. So the result of this reaction is that hydrogen can then enter the material. So an important factor to consider is the presence of hydrogen sulfide from sulfate reducing bacteria, which can act as a catalyst or promoter for hydrogen entry. So I just want to look at a couple of case studies on HISC. So the first is on a 13% chrome line pipe. So on this example, you can clearly see this crack at the fillet weld on a 13 chrome line pipe. So this crack was located at the fillet weld of an anode double plate attachment on the 13 chrome line pipe. And the cracking was due to overprotection from the CP system combined with residual stresses from the fillet weld. So the other example here, you can see that a crack appeared in the field joint coating on the line pipe. When this was investigated, you can see here the crack was actually in the 13 chrome pipe and spanned this girth weld. So the cracking in this example was due to the disbonded field joint, the high stresses at the girth weld, and the overprotection from the CP system, generating an excessive amount of hydrogen. The other example is HISC of a duplex stainless steels. So HISC of duplex stainless steels was first reported in 1996 on the Foynhaven field. So on this example, a 25 chrome super duplex stainless steel hub forging cracked adjacent to a girth weld, as shown on this sketch here. So the applied CP potential, which was applied using a sacrificial aluminium anode, was at minus 1050 millivolts, which resulted in an excess amount of hydrogen being generated. In addition to that, there's high local stresses, which were above 80% of the yield, and a susceptible microstructure where you had large ferrite grains which ran through the wall thickness of this hub. And this photograph shows the HISC here running along the ferrite phase of the duplex structure, and the crack was interrupted by any austenite islands, so it was allowed to extend through the complete wall thickness of the hub. This photograph on the right hand side is not from the failure, but I put it as an example to show how the directionality of the duplex structure and also the austenite spacing has a big influence on preventing HISC. And you can see here we've got a HISC crack that runs through the ferrite phase, is arrested by the austenite, then obviously is delayed, but in this example it finds its way around this austenite island, then continues through the structure, finds its way around this austenite island again, and then is terminated in this region. So how do we prevent HISC? So first is to prevent overprotection by the CP system or minimize hydrogen evolution at the cathode. So the other way is to control the microstructure. So for duplex stainless steels, you need to look at the directionality, the phase balance, the non-metallic phase precipitation, and also limit the nitride phase precipitation. So thirdly, you want to minimize the strength, level and the hardness, and also avoid local stress concentrations and avoid welded anode plate connections. So finally, for duplex stainless steel, there is a recommended practice for HISC, which is RPF112, and this is a design of duplex stainless steel subsea equipment exposed to cathodic protection. So I just want to now move on to microbial influence corrosion and look at the corrosion of copper nickel tubed marine coolers. And these slides have been kindly provided by Robin Oakley of Kinetic, and this presentation was made to the Marine Corrosion Forum in July of 2016. So the investigation found a through-wall pit in a copper nickel marine cooler tubing which had been in service for about 4 months. So related to this failure, the increased deployment of submarines in coastal, warmer and shallower waters, as opposed to the cold North Atlantic, led to an increase in biofouling and cooler tube blockages, as shown here, where you've got a lot of macro fouling around this filter. So to avoid dismantling the coolers to enable mechanical cleaning, a chemical cleaner was utilised to remove and dissolve macro fouling, and the result of the cleaning can be seen in this photograph. So these cleaners were essentially a dilute inhibited hydrochloric acid, and combined with debris removal, they were effective in cleaning the header spaces and cooler tubes. But they also removed the protective surface layer on the tubes. Therefore, conditioning was required before returning the tubes into surface. The absence of a protective surface layer was a possible contributory factor in some recent tube corrosion incidents. So I'm just going to skip the next few slides because of time and just show you the results of the trials that were carried out to combat the MIC, and the trials involved treating coupons with chlorination here, and you can see from this graph the effect of the chlorination treatment. So the treatment here, which was a shock dose of chlorine, which was applied to the system in the harbour, resulted in the SRB bacteria level being reduced by 99.9%, the SGB levels being significantly reduced, and also the level of aerobic bacteria being reduced from 190 to less than 10 CFU per mil. You can see on these graphs the effect of the chlorination treatment in reducing the bacteria count, and thus preventing problems with microbial induced corrosion. So finally, for the next 5 minutes, I just want to quickly look at some examples of corrosion issues with onboard seawater cooling systems. And these slides were kindly provided by Clive Tuck, who's an honorary member of the Marine Corrosion Forum and was formerly with Lloyd's Register. So these slides were presented at the Marine Corrosion Forum meeting in October 2009. So the first example I want to look at is wormhole corrosion on copper nickel iron tube sheets, shown here, and this was caused by this debris and macro fouling on the surface of the tube sheet, which resulted in under deposit corrosion, as shown in this schematic sketch here, where you've got the debris that was collected at the inlet to the tubes, and this resulted in crevices being formed, which consequently resulted in this form of wormhole corrosion or under deposit corrosion. So next example is pitting corrosion of copper, nickel, iron tubes. So shallow pits were formed, which eventually led to perforation of the tubes. So often these pits were located at a uniform distance along the tube from the inlet, as shown on these photographs. So the mechanism of this form of corrosion was considered to be due to under-deposit corrosion, where an area of stagnation resulted at a certain distance from the header of the tube along the length of the tube, and this resulted in deposits accumulating in this region and then resulted in through-wall pitting of the tube. So next example is denuclefication of copper nickel iron tubes, and this occurred under specific conditions, which are high temperatures, a low flow rate, and also is influenced by the presence of sulfate reducing bacteria. So this corrosion mechanism, the copper nickel dissolves locally, and then the copper is redeposited at the surface to give this coppery appearance on the material that you can see on these photographs. So just want to say a few words about galvanic corrosion problems, and many of you probably familiar with the electrochemical series. So this is the electrochemical series showing the corrosion potential of various alloys in seawater. And what you don't want to do is start joining alloys which have a difference in the potential together. This will result in galvanic corrosion. So instead of the electrochemical series or the difference in the corrosion potential, you also need to consider the anode to cathode area ratio, the galvanic current, the temperature, the flow, the presence of dissolved oxygen, any chlorination that's applied, and also the presence of the biofilm. So I've just got a few examples just to finish off. So first is a brass drainage tap shown here, which corroded in this region and fractured. So this was connected to a nickel aluminium bronze pump casing, and it failed after 6 months of service. And the potential difference between the nickel aluminium bronze and the brass was about 200 millivolts. So this was large enough to give you galvanic corrosion. And what made it worse, you had a large cathode, which was the bronze, and a small anode, which was the brass. Second example is a copper nickel iron inlet connection of a titanium heat exchanger, and this corroded around the connected flange and resulted in through wall pitting, causing pipe leakage. So the potential difference between the copper nickel and the titanium was about 300 millivolts, and the pipe connection should have been electrically isolated from the heat exchanger. That is isolated at both ends. So the final example is a super duplex stainless steel nut on a nickel aluminium bronze impeller. So you can see here the duplex stainless steel nut and the impeller. So the nut has not been corroded, whereas the impeller is seeing signs of corrosion. So the potential difference between the duplex and the nickel aluminium bronze was about 200 millivolts. But the cathode was relatively small and the anode was large, and therefore this is not a bad situation to have. So therefore the corrosion was not particularly severe. So that is the end of my presentation. So it's gone a few minutes over the 45 minutes. So I hope that you've enjoyed it, and thank you for taking the time to listen. I'd be pleased to take any questions or comments on the presentation. Thank you.
Thank you very much. Oh yeah.
Oh, thank you.
There we go. Excellent. Good. Thank you very much. So I'm getting an echo. Never mind. There's a quick question in the chat from Dave Weston.